In the heart of the constellation Boötes, astronomers discovered an abyss so colossal and silent that it was nicknamed the Great Void. To give you an idea, if our solar system were there, we probably would have never seen another galaxy in the night sky. It's as if, in the midst of a bustling city, we found an absolute desert where darkness and silence reign. The Boötes Void is not only an astronomical rarity due to its size, it is also an enigma for science. Why does such an immense region exist with so few galaxies when the rest of the universe seems to be sprinkled with them? What forces or processes have emptied this space? Its mere existence forces us to rethink our ideas about the formation of the universe, the distribution of matter, and the influence of phenomena like dark matter and the energy-driving cosmic expansion. Delving into the secrets of the Boötes Void is, in a way, to look into the very abyss of the universe. We face a region where the rules seem to be different, where solitude is the protagonist, and where each galaxy found is a rarity worthy of study. What stories does this void tell us? What does it reveal about the origin, evolution, and fate of the cosmos? Perhaps by contemplating the most uninhabited place in the universe, we will discover new answers about our own existence in this vast cosmic stage. What if I told you that most of the universe is actually an immense void? When we think of the cosmos, we often imagine an ocean filled with stars, galaxies, and planets. But the reality is much more surprising. There are enormous regions where, at first glance, it seems there is absolutely nothing. These areas are called cosmic voids. But what exactly are they? Are they simply empty spaces? Or do they hold much deeper mysteries? In scientific terms, a cosmic void is a vast region of the universe where the density of galaxies is extraordinarily low compared to other, more populated areas. If the universe were a sponge, the voids would be the holes, and the rest, the dense fibers filled with matter. These voids are not completely devoid of matter. They may contain diffuse gas, subatomic particles, and even a few isolated galaxies, but their essential characteristic is the almost total absence of complex cosmic structures. Why do these enormous gaps exist? Their origin is linked to fluctuations in matter density shortly after the Big Bang, when small differences were amplified over time, sculpting a cosmic web of filaments and voids. Some might wonder if these voids affect the behavior of the universe. The answer is a resounding yes. Cosmic voids play a fundamental role in the evolution of galaxies and the expansion of the universe. They act as natural boundaries, separating enormous clusters of galaxies known as superclusters. The differences in density between the filaments and the voids influence local gravity, the movement of galaxies, and even the distribution of dark matter. It is fascinating to think that, although the voids are defined by their apparent lack of content, their presence is key to understanding the structure and fate of the cosmos. Are cosmic voids completely empty? The short answer is no. Although their name may suggest otherwise, even in the most desolate regions of the universe, matter never disappears completely. There are always traces left. Solitary atoms, weak magnetic fields, and occasional bursts of radiation. But the most striking thing is that these vast expanses can measure hundreds of millions of light-years in diameter, making any galaxy trapped within them feel lonelier than we can imagine. Thus, cosmic voids not only define the universal architecture, but also serve as natural laboratories to explore the limits of physics and our understanding of the whole. Where does one of the emptiest regions of the universe hide? If we look up at the night sky from the northern hemisphere, we might think that everything is filled with stars, constellations, and galaxies. However, amid all that brightness, there exists a particularly lonely corner. This place is known as the Boötes Void, and its location has intrigued astronomers for decades. But how do you find something that, by definition, contains almost nothing? The Boötes Void is located in the direction of the constellation Boötes, a recognizable figure by its brightest star, Arcturus. But the curious thing is that while Boötes seems like a beacon in the sky, behind it lies an almost total abyss of matter. To locate the Boötes Void, scientists rely on the projection of constellations onto the celestial sphere, a kind of imaginary map that helps us navigate the cosmos. Although to the human eye, the constellation of Boötes is just a group of stars, for astronomers it represents the gateway to an unimaginably vast emptiness. This void is not exactly within the constellation, but in the same region of the sky it occupies, extending far beyond what the visible stars encompass. It's as if, behind a curtain of lights, there is a vast and dark room where almost nothing interrupts the silence. And how far is this void from us? The Boötes Void is approximately 700 million light-years away from Earth. That means the light that reaches us from the few objects present there has traveled for over 700 million years before reaching us. In terms of scale, it's like trying to locate a bubble of solitude in the cosmic ocean, guiding ourselves only by the direction where the sea seems calmer. Thus, although the void is aligned with the constellation of Boötes in the sky, it actually extends to depths of space unimaginable in our daily lives. A fascinating question is why such a colossal void has formed in that region of the universe. Astronomers have mapped the sky using telescopes capable of detecting galaxies at enormous distances. And when analyzing the distribution of these galaxies, they noticed an area where there is almost nothing. Thus, the location of the Boötes Void was determined not by what we see, but by what is missing. It serves as a reminder that the universe is not just a stage of lights, but also of absences, and that even the emptiest regions can reveal secrets about the deep structure of the cosmos.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
How big can a truly empty region in the universe be? When we talk about the Boötes Void, we encounter dimensions that challenge human imagination. This cosmic void has an approximate diameter of 330 million light-years, which means that if you could travel at the speed of light, it would take you over 300 million years to cross it from one end to the other. To put it in perspective, the Milky Way, our galaxy, measures just about 100,000 light-years in diameter. The Boötes Void is thousands of times larger. It's like comparing a soap bubble to an entire city, but on a cosmic scale. Are there other equally uninhabited regions? In the universe, there are many voids, but most are significantly smaller. The Boötes Void stands out not only for its size, but for its extraordinary absence of matter. In its enormous volume, only a few dozen galaxies have been detected, when the norm would be to find thousands in a region of that size. If the universe were a giant beehive, the Boötes Void would be a nearly completely empty cell, while other cells are filled with honey, that is, with galaxies and matter. But what does it really mean to measure something so immense? Astronomers use the concept of light year to express these distances, as measuring in kilometers or miles makes no sense at these scales. A light year is the distance that light travels in a year, and in that time, light travels almost 10 trillion kilometers. Now, multiply that by over 300 million, and you barely start to grasp the vastness of the Boötes Void. Even galaxy superclusters, which are the most massive structures in the universe, pale in comparison to this void. Could there be something larger and emptier in the cosmos? While there are other notable voids, such as the Eridanus Void, Boötes has been for decades the most extreme example of a region with hardly any galaxies. Its discovery led scientists to rethink how matter is distributed on a large scale and why these gigantic uninhabited spaces exist. Ultimately, the Boötes Void is a reminder that in the universe, emptiness can be even more astonishing than the presence of matter, and its colossal size compels us to reconsider our place in the vastness of the cosmos. How is it possible that one of the emptiest and most mysterious regions of the universe went unnoticed for so long? In the early 1980s, the cosmos still concealed numerous secrets, and the Boötes Void was one of the most striking. Everything changed in 1981 when a group of American astronomers, led by Robert Kirshner, decided to conduct an in-depth study of the distribution of galaxies in the sky, something that at the time was a monumental task. Why search for voids in the universe when the fascinating seem to be where there is more matter? The answer emerged by accident upon noticing a strange absence of galaxies in a wide area during a systematic survey. The discovery was not the result of a stroke of luck or a single night of observation. For several months, the team used optical telescopes to map regions near the constellation of Boötes. What they observed was puzzling. While the rest of the sky was dotted with galaxies, like lights in a city seen from above, that particular strip was a kind of cosmic desert, a silence in the universal bustle. Could it be a mistake in the measurements, or was there really a gigantic empty region? To confirm it, they repeated the surveys and consulted catalogues, always obtaining the same result. The absence of galaxies was real. The news spread quickly through the scientific community. The idea that there was such a large void, comparable to a gigantic bubble within the structure of the universe, challenged the accepted notions at the time about how galaxies are distributed. Was our universe much emptier than we thought, or was it a unique anomaly? The Boötes Void, also known as the Great Void, became a true enigma for cosmologists. Its size, completely unexpected, forced scientists to revise their models of cosmic formation and the behavior of large structures. This discovery, far from closing questions, opened many more. What processes could have given rise to such a void? What does it mean for the evolution of the galaxies that exist at its borders? The finding of 1981 marked a turning point in astronomy, demonstrating that even when we think we know the map of the universe, there are always unexplored regions waiting to be discovered. Sometimes, the most interesting thing is not what is filled with light, but the profound silence of the void. How is it possible to detect such an empty region in a universe full of stars and galaxies? To answer this, we first need to understand that astronomers do not search for these voids with traditional telescopes, as if looking for something bright in the dark. On the contrary, they search for absence, areas where, surprisingly, there is almost nothing. But how do you identify nothing in space? The key is to map the distribution of galaxies, as if studying a forest looking for clearings among the trees. Where astronomers expected to find hundreds of galaxies, they suddenly found a huge gap. The most commonly used method is the galaxy survey. Using telescopes equipped with sensitive detectors, the sky is observed in large strips, and the position, brightness, and distance of each visible galaxy are recorded. When the data is plotted on a three-dimensional map, surprising patterns emerge: filaments, clusters, and of course, voids. The Boötes Void stood out because, in a region where thousands of galaxies should be found, only a few were observed. It's as if, when looking at a city from above, an entire neighborhood without houses or lights was discovered. But how do astronomers determine the depth and true size of this void? This is where redshift comes into play. Each galaxy is moving away from us at a speed that depends on its distance, and this changes the wavelength of the light it emits. By measuring the redshift of thousands of galaxies, scientists can calculate their location in three-dimensional space and thus delineate the exact edges of the void. This technique is like using the echo of a shout in a cave to know how big the unseen space is. In addition to optical observation, astronomers have employed other wavelengths, such as infrared or radio waves, to ensure that the void is not simply an illusion caused by interstellar dust or instrumental limitations. Each new technology has confirmed the existence of the Boötes Void and refined its map. Thus, the set of observational methods becomes a kind of cosmic scanner, capable of revealing the secrets of the largest uninhabited regions of the universe. Have you ever wondered how the universe is organized on gigantic scales? Beyond the stars, galaxies, and clusters we usually imagine, the cosmos is structured like a vast three-dimensional spider web. This cosmic network is made up of filaments of matter, where thousands of galaxies cluster together, and large voids, enormous regions where there is practically nothing. But why does the universe resemble a giant sponge or spider web? The answer lies in the early evolution of the cosmos, when small density fluctuations were amplified under the influence of gravity. The filaments are like cosmic highways, gigantic channels of dark matter and gas, along which galaxies are born and evolve. Galaxy clusters concentrate at the intersections of these filaments, forming true nodes of cosmic activity. And between these filaments, we find the voids, regions so uninhabited that if we could travel through them, we could traverse millions of light years without encountering a single galaxy. The Boötes Void is precisely one of these regions, notable for its size and extreme scarcity of matter. Why do these enormous voids exist? During the formation of the universe, matter was not distributed evenly. Areas with more matter attracted each other and densified, forming filaments and clusters, while other regions remained almost empty, expanding with cosmic expansion. Thus, the voids are a reflection of a constantly changing universe, where gravity and dark energy shape the distribution of everything that exists. Studying the large-scale structure of the universe allows us to understand how galaxies, clusters, and voids formed. Astronomers use enormous three-dimensional maps to analyze the distribution of matter and discover surprising patterns. The Boötes Void, being one of the largest known voids, represents a key piece in this cosmic puzzle, helping us decipher how universal architecture works and how fundamental forces have sculpted the universe we inhabit. How many more secrets do these immense voids in the cosmic web hold? What makes the Boötes Void so special among cosmic voids? To understand it, one must first know that voids in the universe are not as rare as one might think. There are thousands of voids scattered throughout the vast cosmic web, and most of them have considerable dimensions. However, the Boötes Void stands out for its size and its extraordinary lack of matter. While other voids may contain hundreds or even thousands of dispersed galaxies, Boötes is famous for its almost complete absence of them. It's as if, among the bubbles of the universe, this one is especially large and nearly completely empty. Is it possible to compare the Boötes Void with other known voids? Of course. Let's take, for example, the Eridanus Void, another of the great cosmic voids. Although Eridanus is also impressive and has drawn attention due to the anomalies associated with the cosmic microwave background, its extent and desolation do not reach the extremes of Boötes. Most voids typically measure between 20 and 50 million light-years in diameter, but the Boötes Void far exceeds those figures, housing within it a volume so large that it could contain several galaxy superclusters and still have space left over. Another essential difference is the relative density of galaxies. In many voids, although the density of matter is low, it is not unusual to find faint filaments and small groupings of galaxies that remind us that even in the void, matter finds ways to gather. However, in Boötes, only a few solitary galaxies have been identified, so isolated from each other that if each were an island, the oceans separating them would be practically infinite. This level of isolation is not common even among the largest known voids. So, why is the Boötes Void so extreme? Astronomers have wondered if it could be a primordial void, that is, a region that never formed significant structures for reasons that are still being investigated today. Some models suggest that random processes in the early stages of the universe's formation may have generated voids of various sizes, but the magnitude and uniformity of Boötes make it an outlier. To this day, it remains an enigma that challenges conventional explanations and places it in a category of its own, that of the extreme large voids, where nothing seems to be the absolute protagonist. Is it possible that in such a desolate region of the universe as the Boötes Void, there are galaxies? At first glance, it would seem that such a vast and empty place should be completely devoid of any kind of galactic structure. However, the reality is even more fascinating. Within this cosmic abyss, astronomers have identified the presence of a few solitary galaxies, true castaways in an ocean of nothingness. These galaxies challenge our intuition about how matter should behave at the edges of the void and invite us to question how far the universe's capacity to surprise us extends. What makes these solitary galaxies so special? Unlike their counterparts in regions filled with matter, the galaxies of the Boötes Void live in isolation, without the company of nearby clusters or the protection of galactic filaments. They are like beacons lit in the midst of the darkest night, evolving independently for billions of years. This extreme loneliness has notable consequences. The lack of gravitational interactions with other galaxies means that their shapes are often irregular and their star formation processes are much slower. Some have retained primitive structures, almost intact since the early times of the universe. What are these galaxies made of? For the most part, they contain much less gas and dust than galaxies situated in denser environments. The limited access to raw materials for forming new stars has slowed their evolution, making them natural laboratories to study how galaxies behave under extreme conditions. Astronomers believe that, due to the scarcity of surrounding gravity, these galaxies have avoided chaotic mergers and violent encounters, maintaining characteristics that would have disappeared elsewhere. This allows scientists to observe galactic processes in an almost pure state, as if they were looking back in time. But there's more. How did these galaxies end up there? There are several theories. One possibility is that they formed within the void itself, from small fluctuations of matter that managed to overcome the immense scarcity of material. Another hypothesis suggests that, at some point, these galaxies were part of denser regions and, due to the expansion of the universe, were expelled into the void, drifting aimlessly. Whatever the origin, each solitary galaxy found in the Boötes Void is a silent testament to the diversity and complexity of the cosmos. They are reminders that, even in the most inhospitable places and seemingly devoid of life, the universe always holds surprises waiting to be discovered. Talking about the scale of the Boötes Void is to confront figures that challenge our imagination. How large can an empty region in the universe be? The Boötes Void has an approximate diameter of 330 million light-years. To put it in perspective, the Milky Way, our galaxy, measures just about 100,000 light-years in diameter. If the Milky Way were a small coin, the Boötes Void would be like a sphere the size of an entire city. It is such a vast expanse that if we could travel at the speed of light, it would take us more than 300 million years to cross it from one end to the other. What does this mean in cosmic terms? While most regions of the universe are filled with galaxies, clusters, and dark matter, the Boötes Void is extraordinarily desolate. Inside it, astronomers have detected only about 60 galaxies, when the norm would be to find thousands in a similar region. It's like entering a gigantic stadium and discovering that, instead of a crowd, there are only a handful of people scattered in the stands. The proportion of emptiness is so overwhelming that it is considered one of the least dense areas ever observed by humanity. When we compare the Boötes Void with other known voids, its magnitude remains impressive. For example, the distance between Earth and the Andromeda Galaxy, the closest neighbor to the Milky Way, is just 2.5 million light-years. In contrast, the Boötes Void is more than 100 times larger than that distance. Even galaxy superclusters, which are the densest and most massive structures in the universe, seem small compared to the immensity of the void. This colossal scale not only impresses with its size but also with what it represents, a true anomaly in the architecture of the universe. Why does such a gigantic and empty region exist? What cosmic processes could have cleared matter from such an extensive space? The Boötes Void forces us to rethink our ideas about the distribution of matter, challenging the concept of uniformity and reminding us that, even in the universe, emptiness can be as astonishing as what is filled with stars and galaxies. Did you know that most of the matter in the universe is something we cannot see or touch? We call this mysterious substance dark matter. But what does dark matter have to do with cosmic voids like the Boötes Void? To understand this, we first need to imagine the universe as a gigantic three-dimensional web, similar to a spider's web, where the thickest strands are made up of galaxies and clusters, and the empty spaces between them are the so-called cosmic voids. Dark matter is like the invisible skeleton that supports this entire structure. Although it does not emit light or detectable energy, its gravity is essential for the existence of the filaments, and consequently, the voids. But why do these enormous gaps exist? The key lies in how dark matter influences the evolution of the cosmos. When the universe was young, regions with a higher concentration of dark matter attracted more ordinary matter, forming galaxies and clusters. On the other hand, areas with less dark matter became increasingly empty because visible matter was drawn towards the denser regions. Thus, voids like Boötes are the result of a kind of gravitational expulsion, where the absence of dark matter prevents the formation of cosmic structures. An intriguing question is there dark matter within the voids, or are they completely empty of this substance as well? Studies indicate that although the density of dark matter in the voids is much lower than in the filaments, it is not an absolute void. Imagine it as a huge pool that is almost empty, with just a few drops of water left. In the case of the Boötes Void, the amount of dark matter is so low that it cannot attract enough gas and dust to form galaxies, but it is not non-existent either. In fact, it is thought that the residual presence of dark matter could explain the existence of the few solitary galaxies found within these voids. The relationship between dark matter and the voids is fundamental to understanding the large-scale evolution of the universe. If dark matter did not exist, the universe would be much more homogeneous, and we would not have these immense uninhabited regions. Studying voids like Boötes helps scientists test current theories about dark matter and its role in cosmic architecture. Could we be on the verge of a key clue to decipher one of the greatest enigmas of the cosmos? Each new piece of data about these voids brings us a little closer to understanding the deep nature of that invisible matter which, although we cannot see it, shapes the universe at will. How is it possible for astronomers to understand such immense and empty regions like the Boötes Void? The answer lies in the power of cosmological simulations. These computational models, which require supercomputers capable of processing colossal amounts of information, allow scientists to recreate the universe from its earliest moments to the present day. But what do these simulations really consist of? Basically, the known physical laws, the initial conditions after the Big Bang are introduced, and from there, gravity, matter, and energy are allowed to evolve over billions of virtual years. It's like watching a sped-up movie of the cosmos, where the protagonists are galaxies, clusters, filaments, and of course, gigantic voids. One of the great surprises of these simulations is that even starting from a relatively homogeneous, primitive universe, matter does not distribute evenly over time. The small initial fluctuations grow and amplify, forming a cosmic web of filaments where matter clusters, and enormous empty bubbles where there is almost nothing. The Boötes Void appears repeatedly in these models as an extreme example of these large gaps. This means that its existence is not an accident or an anomaly, but a natural consequence of how gravity works on a large scale. It's as if the universe were a sponge, where the gaps inevitably form among the frameworks of matter. But how is it verified that these simulations reflect reality? Astronomers compare the predictions of their models with real observations. The distribution of galaxies, the shape and size of the voids, even the amount and type of matter at their edges. If a simulation manages to recreate a void as large and sparse of galaxies as Boötes, it is a sign that the ingredients and laws introduced in the model are correct. However, when discrepancies arise, new questions emerge. Is there something we don't understand about dark matter? Or perhaps dark energy plays a different role than we thought? Cosmological simulations not only help explain the formation of voids, but they also allow exploring scenarios impossible to reproduce in traditional experiments. For example, one can modify the amount of dark matter or alter the rate of expansion of the universe to see how the resulting voids change. Thus, scientists can rule out theories and refine their models until they fit with the observed reality. Ultimately, these virtual experiments are like laboratories of the universe, where the Boötes Void is a key piece to understanding the history and evolution of everything that exists. What could cause such an immense void in the universe as the Boötes Void? To answer this question, we must first understand how matter is distributed on a large scale. The universe, far from being homogeneous, presents a structure resembling a gigantic cosmic web, where matter accumulates in filaments and nodes, leaving vast spaces between them that are practically devoid of galaxies. The Boötes Void is one of these gaps, but its size is so colossal that it challenges simple explanations. Why is there such a vast and empty region, surrounded by a sea of galaxies and clusters? The most accepted explanation among astronomers points to the quantum fluctuations that occurred moments after the Big Bang. Imagine the early universe as an extremely hot and dense soup, where small variations in density were amplified over time. Some areas, slightly denser, attracted more matter and became the future filaments and superclusters. In contrast, other areas, with less density, failed to attract enough matter and ended up becoming voids. The Boötes Void would then be the result of one of these less dense regions, where matter never accumulated like in other parts of the cosmos. But why is Boötes so exceptional? Cosmological models show that voids appear naturally, but the magnitude of the Boötes Void continues to draw attention. Some scientists have suggested the possibility that several smaller voids may have merged over billions of years, forming a supervoid. It's as if several bubbles in a foam joined together, creating a single gigantic bubble. This process of void merging could explain the enormous extent of Boötes. Another intriguing question is whether there are even stranger phenomena behind the formation of the Boötes Void. Could dark matter or dark energy have influenced this region in a special way? Although there is still no conclusive evidence, research is underway to determine if local variations in dark matter distribution may have contributed to the expansion of the void, preventing galaxy formation within it. However, so far, the most solid hypothesis remains the natural development of cosmic structures from the seeds sown in the early moments of the universe. Thus, the existence of the Boötes Void is a combination of cosmic chance and fundamental physical laws. It reminds us that the universe is not uniform, but rather the result of complex processes that generate both crowded regions of galaxies and deep abysses of spatial solitude. The mystery of why the Boötes Void exists continues to motivate astronomers to seek answers, showing that even in apparent emptiness, the cosmos holds fascinating stories about its origin and evolution. What happens when the universe expands? Most people imagine that galaxies simply move away from each other in empty space, but the reality is even more fascinating. The expansion of the universe not only separates galaxies, it also stretches the very space between them. And this process has a fundamental effect on the formation of regions like the Boötes Void. If the universe were not expanding, cosmic voids would be much smaller or even non-existent. Why? Because matter, under the influence of gravity, would tend to distribute itself more evenly, filling the gaps over time. But how does expansion contribute to the existence of such vast and uninhabited regions as the Boötes Void? Imagine a mass of dough that is fermenting. As the dough rises, the air bubbles inside expand and move away from each other, creating increasingly larger and emptier spaces between them. Similarly, cosmic expansion stretches regions of the universe, amplifying voids and further separating galaxies that were once closer together. Thus, voids are not simply static gaps. They are spaces that enlarge as the universe ages. An intriguing question arises here. Will voids like Boötes continue to grow forever? The answer is related to dark energy, that mysterious force driving the accelerated expansion of the universe. As dark energy dominates cosmic destiny, voids expand at an ever-increasing rate, pushing matter towards the filaments and superclusters that form the large-scale structure. This dynamic turns voids into silent protagonists of universal history. Their growth is, in fact, a visible footprint of the expansion of space itself. This process has surprising consequences. The expansion of the universe not only creates more emptiness, but also determines how galaxies and clusters evolve. At the edges of voids, matter accumulates, but inside them, solitude intensifies. The Boötes Void is a testament to how expansion can sculpt unimaginable cosmic landscapes, where space, far from being just a backdrop, becomes the true architect of the universe. By observing these enormous voids, astronomers can study not only the distribution of matter, but also the deep rhythms with which the cosmos expands and transforms. What lies at the edge of a cosmic void? When thinking of the Boötes Void, we might imagine an immense dark sea, but even a sea needs to have shores. Where does this abyss end, and where does the rest of the universe begin? The boundary of the Boötes Void is much more than a simple line separating the empty from the full. It is a transitional region that challenges our understanding of cosmic structure. The edge of this void is like the rim of a giant bubble in space, where the density of galaxies increases abruptly. While inside the void, we find only a few solitary galaxies. At the borders, there is a kind of galactic wall, an accumulation of matter that marks the limit between nothingness and abundance. This transition does not occur instantaneously. Rather, it extends over millions of light years, forming a gradient zone where density gradually increases. It is in this region where galactic filaments seem to intertwine, feeding the universe with matter and energy. How does matter behave near this boundary? Astronomers have discovered that, at the edges of voids like Boötes, gravity plays a fundamental role. The galaxies located at the boundary tend to cluster and form more compact structures, as if the lack of matter in the void pushes them outward, concentrating at the limits. It is a phenomenon similar to what happens when soap bubbles cluster and share thin walls, separating the air inside from the outside. Here, the boundary not only divides nothing from everything, it also defines how large cosmic structures are organized. Could there be something special about these edges that we do not yet understand? The limits of the Boötes Void are natural laboratories for studying the evolution of the universe on a grand scale. In these margins, scientists seek clues about dark matter, dark energy, and the dynamics of galactic filaments. The differences in the distribution of matter along the edge may reveal secrets about the processes that shape the universe since its origins. Each void boundary is, in fact, a testament to the eternal tug-of-war between expansion and gravity, nothingness and cosmic creation. Thus, the boundary of the Boötes Void reminds us that the universe is neither homogeneous nor symmetrical. The limits between voids and filaments are zones of tension and change, where the cosmos builds its most impressive structures. Exploring these edges is to delve into the very essence of how the universe organizes and evolves, showing us that even in the vastness of the void, there is always something fascinating waiting to be discovered. In the heart of the Boötes Void, one of the most desolate regions of the universe, a fascinating enigma arises. How is it possible for completely solitary galaxies to exist in a place where there is practically nothing? This mystery has puzzled astronomers since the discovery of the first isolated galaxies within this gigantic void. Unlike the galaxies we know, surrounded by neighbors and forming part of groups or clusters, these few survivors seem to defy logic, floating in a sea of almost absolute cosmic solitude. What are these galaxies made of, and what sets them apart from their counterparts in denser regions? Surprisingly, some of these solitary galaxies exhibit unusual characteristics. They are smaller, less luminous, and in many cases show a dramatic scarcity of heavy elements, indicating that they have had few opportunities to interact with other galaxies and form new stars. It is as if they have been forgotten by the rest of the universe, remaining in a kind of galactic slumber for billions of years. But how did they get there? Did they form in the void, or were they expelled from richer regions? The most accepted theory suggests that some of these galaxies were born in the void itself, from small fluctuations of matter that failed to join the large galactic filaments. Others may have been dragged into the void by gravitational processes, becoming trapped in their isolation. The most intriguing aspect is that, being so far from other galaxies, these cosmic islands evolve almost independently, without the mergers and violent encounters that shape galactic life in the rest of the observable universe. Is it possible that within these isolated galaxies there are solar systems as lonely as they are? The answer is yes, but the odds of finding life in such a resource-poor and stimulus-deprived environment are extremely low. The distance between one star and another can be immense, and the galaxy itself may lack the necessary ingredients for the formation of complex planets. However, the mere existence of these galaxies demonstrates the astonishing diversity and adaptability of the universe. They are silent witnesses to a cosmos where, even in the most inhospitable and empty places, matter resists complete disappearance and continues its slow, silent evolution. What would we see if we could embark on a journey through the Boötes Void? The first thing that catches the eye is the overwhelming absence. Unlike almost any other corner of the observable universe, here the vastness is dominated by silence and darkness. In most directions, there would be no galaxies shining on the horizon or swarms of stars competing for our attention. Instead, we would find ourselves surrounded by an ocean of blackness, so deep and vast that it might seem like we are floating in a bubble of absolute nothingness. Could we find any sign of life? Any hint of cosmic activity? The answer is surprising. Within the Boötes Void, galaxies are as rare as solitary islands in an infinite sea. If we traveled for millions of light years in any direction, we might only stumble upon one or two scattered galaxies, each isolated, evolving in solitude. These galaxies would be small, sparsely populated, and likely very different from those that are part of galactic clusters. How does this isolation affect their development? Astronomers believe that, far from the gravitational influence of their neighbors, these solitary galaxies evolve with an unusual calm, escaping the mergers and collisions that are common in denser regions. And what would the visual experience of traversing this region be like? Instead of the typical starry background, the sky would be emptier than ever. The number of stars visible to the naked eye would drastically decrease. Space would seem even colder and more desolate, as if light itself refused to penetrate the vastness of the void. The feeling might resemble being in the midst of an infinite desert, where there are no references, no mountains, no trees, just the endless expanse of nothingness. But, although the landscape is almost completely dark, the reality is that there are still particles, radiation, and, of course, the omnipresent dark matter, invisible yet present. If any hypothetical ship attempted to cross the Boötes Void, the journey would be overwhelmingly lonely. With no nearby stars for navigation, finding one's way would be a monumental challenge. Even the light from the nearest galaxies would take millions of years to arrive. Is it possible that in such an extreme environment, the perception of time and space changes? Some scientists believe that traveling through a void of such dimensions would make us understand, like nowhere else, the true scale of the universe and the smallness of our own existence. Ultimately, a journey through the Boötes Void would not only be a physical crossing, but also a profound reminder of how insignificant and strange the cosmos can be. Could life exist in a place as empty and desolate as the Boötes Void? To answer this question, we must first consider what life, as we know it, needs to arise and develop. On Earth, the fundamental ingredients are matter, energy, and above all, the interaction between atoms and molecules in a relatively dense environment. But the Boötes Void is radically opposite. It is a region of the universe where the density of matter is incredibly low, so much so that it could be compared to trying to find a needle in an ocean. But without the ocean, just the void. In the Boötes Void, not only are galaxies scarce, but also the basic elements like hydrogen and helium, the fundamental building blocks for the formation of stars and planets. While there are a few solitary galaxies, the distance between them is so overwhelmingly vast that the probability of them interacting or sharing matter is virtually zero. Could life emerge in a region where there is so little matter that even the light from stars is a rare and distant visitor? The answer, according to scientists, is that the conditions are so extreme that life, at least in forms we can imagine, would have enormous difficulties appearing. Let's consider, for example, energy resources. In the Boötes Void, cosmic background radiation is practically the only available energy source, but its intensity is so low that it could not sustain even the simplest processes of terrestrial biochemistry. Moreover, the almost total absence of heavy elements, such as carbon, oxygen, or nitrogen, further limits the possibility of forming complex molecules essential for life. It's like trying to spark a flame in a space where there is neither oxygen nor fuel. What if there were completely different forms of life than those we know, perhaps based on unknown processes or exotic chemistry? While science never completely rules out the unknown, the Boötes Void represents such an inhospitable environment that even the boldest hypotheses face challenges. The vastness of the void, the solitude of its galaxies, and the lack of matter and energy make this place one of the least favorable scenarios for life in the entire cosmos. Thus, the Boötes Void reminds us that although the universe is vast and mysterious, not all its corners are fertile or welcoming for the emergence of life. What happens when a region of the universe is almost empty of matter? The Boötes Void is the perfect setting to explore this question, as inside it, matter is strikingly absent. Gravity, that force that holds galaxies, stars, and planets together, directly depends on the amount of mass present. But what happens when that mass is scarce to the extreme? In places like the Boötes Void, the gravitational force is so weak that it becomes almost insignificant compared to the more populated areas of the cosmos. If we imagine the universe as a gigantic elastic sheet, where heavy balls represent galaxies and clusters, the voids would be those areas with barely any weight, hardly any depression. In the Boötes Void, the lack of balls means that the sheet hardly deforms there. The curvature of space-time is minimal, and the gravitational attraction is so low that any object within the void will not be pulled in any particular direction. This implies that the few galaxies present can spend billions of years with hardly any interaction with others, as if they were floating in a vast, calm ocean. And how does this affect the dynamics of the universe? In densely populated regions, gravity acts like a magnet, clustering matter and fostering the formation of new stars and galaxies. But in the Boötes Void, the opposite occurs. The scarcity of mass means that the growth and evolution of cosmic structures slows down to a crawl. The solitary galaxies within this void are doomed to an isolated existence, with no nearby neighbors to attract or influence their development. In a way, the Boötes Void is like a gravitational desert, where the force that shapes the universe has barely any effect. Could a spacecraft notice the difference if it traversed the Boötes Void? Although the ship would still be under the influence of the universe's gravity, it would experience a notable lack of acceleration towards any specific point, as if traveling through a territory without hills or valleys. This extreme void is a showcase of the astonishing contrast that exist in the cosmos. While some regions are dominated by the attraction of enormous clusters, others, like Boötes, are spaces where gravity leaves hardly a mark. Thus, the Boötes Void reminds us that the structure of the universe is defined as much by the presence of matter as by its absence, and that sometimes the emptiest places can teach us a lot about the fundamental forces that govern the cosmos. What if we could read the oldest story of the universe, written in a kind of echo that travels through the cosmos? That echo exists. It is the cosmic microwave background, a faint and uniform radiation that fills all of space, a silent witness to the Big Bang. But what does this radiation have to do with the Boötes Void? Scientists have discovered that large voids like Boötes can leave subtle traces in the cosmic microwave background, slightly altering the temperature of that ancient radiation, which, like carbon paper, records the events and structures it has passed through. To understand this, let's think of the cosmic microwave background as a sheet stretched over the universe. When this sheet passes through dense regions, like galaxy clusters, or almost empty areas like Boötes, it experiences small temperature changes, just a few millionths of a degree. This phenomenon is known as the integrated Sachs-Wolf effect. Essentially, the photons that cross the Boötes void are affected by the accelerated expansion of the universe and the scarcity of matter, altering their energy in a minimal but measurable way. Astronomers have thus detected cold spots that correspond with the location of gigantic cosmic voids, as if the void left a faint digital fingerprint on the primordial radiation. Now, is the Boötes void responsible for any notable anomaly in the cosmic microwave background? For years, researchers have debated the existence of a super cold spot, a region of the background that is colder than expected and seems to partially coincide with the position of Boötes. However, the exact relationship remains a matter of controversy. Is it just a coincidence, or has the void truly left a deep mark on the echo of the Big Bang? This question has driven numerous studies, combining galaxy maps and microwave analyses to try to decipher the enigma. Why is this so important? Because studying the traces that voids leave in the cosmic microwave background helps us test theories about the evolution of the universe, accelerated expansion, and the influence of dark energy. Moreover, it reinforces the idea that the universe is not a homogeneous place, but a complex tapestry of filaments and voids that interact with the oldest radiation. Thus, every time scientists find an anomaly or unexpected pattern in the cosmic background, they are unraveling not only the history of regions like Boötes, but also the deepest secrets of the cosmos. What role does the Boötes void play in modern cosmology? This immense cosmic desert is much more than a mere astronomical curiosity. It has become a key piece for understanding the structure and evolution of the universe on a large scale. Voids like Boötes are natural laboratories that allow scientists to test the most advanced theories about galaxy formation, dark matter, and the accelerated expansion of the cosmos. By studying these nearly empty regions, astronomers can observe how matter clusters into filaments and clusters, and how gravity and fundamental forces shape the universal landscape. But why are voids so important to cosmologists? In the standard model of cosmology, the universe resembles a gigantic cosmic web, where voids are the large spaces between the strands of that web. This structure, known as the cosmic web, has been confirmed by observations of galaxies and the cosmic microwave background radiation. Voids, like Boötes, provide a privileged environment to detect small deviations in matter density and to explore the effects of dark energy, that mysterious force driving the accelerated expansion of the universe. Analyzing voids allows us to check whether our theories about the formation of cosmic structures really work at all scales. Moreover, cosmic voids challenge more conservative models and force scientists to refine their hypotheses. Could the existence of such empty regions be a sign of new, yet unknown physics? Some hypotheses suggest that anomalies in the distribution of matter, like the Boötes void, could be indications of primordial fluctuations that occurred shortly after the Big Bang, or even of unexpected interactions between visible matter and dark matter. Therefore, voids are not just spaces without galaxies, but also open doors to fundamental questions about the origin and fate of the universe. Finally, the study of voids like Boötes has driven the development of increasingly sophisticated tools and simulations. Thanks to them, astronomers can recreate the evolution of the universe on supercomputers and compare the results with what they actually observe. If the simulated voids resemble the real ones, the theories gain strength. If not, it's time to revisit what we think we know. Thus, the Boötes void has transformed from a simple hole in the star map to a leading actor in modern cosmology, challenging and enriching our understanding of the cosmos. Have you ever wondered what the emptiest places in the universe are? When we talk about cosmic voids, we refer to regions so vast and devoid of matter that they challenge the imagination. The Boötes Void is one of the most impressive examples, but is it really the absolute champion of voids? To answer that, we need to put things into perspective and compare the cosmic records of desolation. The Boötes Void spans approximately 330 million light-years in diameter. If we wanted to cross it traveling at the speed of light, it would take us over 300 million years. To put it into perspective, the Milky Way is only about 100,000 light-years wide, so we could fit thousands of galaxies like ours within this void and still have space left over. However, Boötes is not the only one on the podium. Other voids, such as the Eridanus Void or the KBC Void, also compete for the title of the most uninhabited region of the universe. The KBC Void, for example, is comparably sized, and some studies even suggest it could be even larger, although less defined at its edges. So what makes the Boötes Void so special? The difference is not just in size, but in contrast to its surroundings. While many voids are surrounded by equally low-density areas, Boötes stands out for being embedded in a region where the density of galaxies is notably higher around it. It's like finding a desert in the middle of a dense forest. The void stands out much more, and its presence becomes even more mysterious. Despite the colossal dimensions of other voids, few present such an abrupt contrast between nothingness and galactic bustle. Why do these extreme voids exist? Astronomers believe they are a direct consequence of how matter was distributed after the Big Bang. As the universe expanded, small fluctuations in the initial density gave rise to a kind of cosmic foam, where galaxies and clusters group into filaments and walls, leaving large empty bubbles between them. This large-scale structure repeats throughout the cosmos, but voids like Boötes are so extensive and so devoid of matter that they remain subjects of debate and wonder. Some scientists even suggest that we might be unaware of even larger voids, invisible to our current observational methods. In the ranking of cosmic voids, the Boötes Void remains one of the most iconic extreme emptinesses. Its discovery not only broke records for its dimensions, but also led to a re-evaluation of how we understand the distribution of matter on a large scale. Every time astronomers find an even larger void, we face the question of how far emptiness can reach in the universe. Are there even lonelier regions waiting to be discovered? For now, Boötes stands as a symbol of cosmic extremes, reminding us that most of the universe is paradoxically empty space. The theory of cosmic inflation is one of the most fascinating ideas to explain the origin of giant voids like the Boötes Void. How could the universe, which we see today as so structured, have emerged from such a uniform state? Scientists propose that in the first moments after the Big Bang, the cosmos experienced an extremely rapid expansion, much faster than the speed of light. This process, known as inflation, would have inflated space in a tiny fraction of a second, stretching any microscopic irregularity to colossal dimensions. But what does this have to do with the voids? During inflation, small quantum fluctuations in the density of the primordial universe were greatly amplified. Some regions ended up with more matter, giving rise to clusters and filaments, while others became almost empty, turning into the great cosmic voids we observe today. It's like inflating a balloon with small spots. As it expands, those spots become huge differentiated areas. The Boötes Void is an impressive example of these regions, a gigantic footprint of inflation, where matter simply did not gather into large structures. This theory not only explains the existence of voids, but also resolves several mysteries of the early universe. For example, why is the universe so homogeneous in all directions? Inflation would have mixed and smoothed out any initial differences, allowing the cosmos to have the same temperature and density in regions separated by inconceivable distances. At the same time, those tiny initial differences, magnified by inflation, seeded the pattern of voids and structures that form the cosmic web. Without inflation, it would be extremely difficult to justify the presence of gigantic voids like Boötes. Why do such empty regions exist alongside others so densely populated with galaxies? The answer lies in quantum chance and the brutal expansion of space. Thus, each cosmic void is a kind of fossil, a silent testimony to the tumultuous first seconds of the universe. Studying these voids not only tells us about what is missing, but also about how everything else came to exist. Is it possible that the universe, in its vastness, resembles more a foam of bubbles than a uniform and continuous space? This idea, which may sound strange at first, is one of the most useful analogies for understanding the large-scale structure of the cosmos. If we could pull back far enough, we would see that the universe is not distributed homogeneously, but rather organized in a kind of web, where large voids like the Boötes Void resemble the bubbles of a gigantic cosmic foam. Between these bubbles, the filaments and walls of galaxies would form the thin membranes that separate them, concentrating most of the visible matter. What accounts for this peculiar structure? The answer lies in the evolution of the universe itself. After the Big Bang, small fluctuations in the density of primordial matter began to amplify due to gravity. Regions that were slightly denser attracted more matter, forming clusters and filaments, while less dense areas became even emptier, expanding into the vast voids we observe today. Thus, the universe developed an appearance similar to that of a honeycomb or foam, where the bubbles represent the large voids and the walls, the concentrations of galaxies and matter. But why is the bubble analogy used so much? Because it helps visualize how the voids are not just simple, empty and isolated spaces, but regions that interact with each other and with the filaments surrounding them. The boundaries between these voids can be quite defined, and at times, the bubbles themselves can merge, grow, or deform as the universe expands. The Boötes Void, for example, would be one of these gigantic bubbles amidst a vast network of void and matter. This bubbling vision suggests that the void is not an anomaly, but a natural consequence of how matter groups on a large scale. This perspective transforms our understanding of the universe. Does this mean that our cosmic home is literally on a foam membrane? In a sense, yes. Our galaxy is part of a filament, a kind of wall between voids, as if we inhabit the thin boundary that separates two bubbles in a glass of soapy water. This image, besides being surprising, allows scientists to create simulations and models to study the evolution of the cosmos, and invites us to rethink what the void really means. Perhaps what seems like an absolutely empty space is actually a fundamental piece in the puzzle of universal structure. What mysterious force is pushing the universe to expand faster and faster? The answer is one of the greatest enigmas of modern physics: dark energy. Although its name suggests an exotic component, dark energy is not something we can see or touch, but its effects are undeniable and are particularly felt in regions like the Boötes Void. This energy constitutes approximately 70% of the total content of the cosmos and acts like a kind of anti-gravity, accelerating universal expansion and further separating visible matter. Why is dark energy so related to cosmic voids? Imagine the universe as a giant sponge with dense filaments of galaxies and huge gaps, the voids in between. In these voids, where matter is almost non-existent, dark energy can act unobstructed. There isn't enough gravity to contain its push, so these regions expand faster than densely populated areas. It's as if the universe, in its most uninhabited areas, allows dark energy to take center stage and stretch space almost without resistance. The Boötes Void thus becomes a natural laboratory to study the effects of dark energy. Astronomers have observed that, compared to other regions of the universe, the expansion of space within voids like Boötes is slightly more accelerated. This suggests that dark energy not only influences the global scale of the cosmos, but also shapes the evolution and size of voids, pushing their boundaries and emptying their interiors even more. Could dark energy be responsible for the existence of extreme voids like Boötes? The answer, although still incomplete, points in that direction. Cosmological simulations show that as the universe ages and dark energy becomes dominant, voids expand and galactic filaments move further apart. In other words, in the future, the Boötes Void will be even emptier, and the mysteries of dark energy will continue to grow alongside it. The role of this invisible force not only redefines our understanding of space, but transforms the very fabric of the universe. What happens when we talk about baryonic matter in the context of the Boötes Void? Baryonic matter is, in simple terms, the normal matter. Atoms, protons, and neutrons that make up everything we can touch, see, or directly measure. It is what composes stars, planets, interstellar dust, and of course, our own cells. However, the Boötes Void is a region where this matter seems almost absent. Why is there so little baryonic matter in this place? What processes led to the fact that, in such an immense volume, there are almost no galaxies or clouds of gas? To understand this, let's think of the universe as a giant sponge. In a sponge, most of the volume is occupied by holes, and only a small part corresponds to solid matter. Something similar happens in the cosmos. The voids are those large spaces between the filaments, where baryonic matter is so scarce that if we condensed all that exists in the Boötes Void, we would barely manage to form a few scattered galaxies. In comparison, the regions of the filaments and superclusters are packed with baryonic matter, creating true galactic cities. This raises a fascinating question. Why is baryonic matter concentrated in certain regions and leaves others practically empty, like Boötes? The answer lies in the early moments of the universe. After the Big Bang, small fluctuations in the density of matter shaped the cosmic structure. Where the density was slightly higher, gravity attracted more matter, forming filaments and clusters. Where the initial density was lower, baryonic matter moved away, leaving behind those enormous voids. Thus, the Boötes Void is the extreme result of this process, a region where, from the very beginning, baryonic matter was practically expelled or never accumulated in large amounts. Another intriguing question is how the scarce baryonic matter survives within the void. The few galaxies found in Boötes are true cosmic castaways, isolated from their nearest neighbors by unimaginable distances. Being so far from other sources of matter, these galaxies evolve in unique ways, often with very little gas to form new stars. It's as if we lived on a lonely island, surrounded by an ocean of void, with barely any resources to survive. The study of baryonic matter in the Boötes Void not only reveals the extremes of cosmic structure, but also helps us better understand how ordinary matter is distributed in the universe, and what the limits are for the formation of galaxies and stars. What happens when two invisible giants, voids, and cosmic filaments meet in the vastness of the universe? The answer is a subtle, yet fundamental cosmic dance that shapes the distribution of galaxies and matter on unimaginable scales. Voids, like that of Boötes, are not simply empty gaps in nothingness. They are actually surrounded and defined by extensive networks of filaments, true galactic highways where matter clusters and travels. The filaments, formed by galaxies, gas, and largely dark matter, act like the walls of a bubble, with the voids being the air inside. Why is this relationship so important? The key lies in gravitational interaction. The filaments exert a kind of pressure on the voids, defining their size and expansion. It's as if the filaments are the edges of a fishing net, and the voids are the spaces between its taut strings. As the universe expands, the voids tend to grow, pushing matter towards the filaments. This process, called void flow, causes galaxies near the edges of the voids to be pushed towards denser regions, further reinforcing the filamentary structure. Thus, voids and filaments do not exist in isolation. They mutually depend on each other to shape the cosmic architecture. Can a void like Boötes alter the evolution of the surrounding filaments? Yes, and in fact, the relationship is reciprocal. When a void grows, it can distort or even fragment the adjacent filaments, changing the dynamics of the galaxies that inhabit them. In turn, the filaments can slow the growth of a void, maintaining a delicate balance. This give and take is essential for understanding how galaxy clusters form and evolve, and why there are such extremely empty regions alongside surprisingly dense areas. It is fascinating to think that, at its core, the structure of the universe resembles a three-dimensional sponge, where voids and filaments are the gaps and walls that constitute it. Without the interaction between the two, the universe would not resemble a gigantic spider web, but rather a uniform and chaotic soup. Unique phenomena develop at the boundaries between voids and filaments: the formation of new galaxies, the acceleration of gas flows, and sometimes the creation of bridges of matter that connect distant regions. Thus, voids like Boötes are not merely places devoid of matter, but key players in the grand cosmic theatre, where each interaction leaves a mark on the evolution of the universe itself. What happens when a galaxy is located at the edges of a colossal void like Boötes? This particular environment, almost devoid of matter, exerts a profound and counterintuitive influence on the fate of the surrounding galaxies. Far from the action of dense superclusters, the galaxies near the void experience a cosmic isolation that shapes their evolution. In dense areas, interactions between galaxies are frequent. Collisions, mergers, and gas thefts are part of the routine. But at the edges of the void, the landscape is different. Can a galaxy thrive if it is so alone? Galaxies situated on the periphery of the Boötes Void experience fewer encounters with other galaxies, drastically reducing galactic mergers. This isolation slows their evolution, as mergers often trigger bursts of star formation and transform the internal structure of the involved galaxies. Without those encounters, many edge galaxies maintain well-defined spiral shapes for billions of years, as if galactic time moves more slowly. It's as if they are in a quiet neighborhood of the cosmic city, far from the hustle and bustle where things change incessantly. In contrast, the scarcity of matter in the void also means that gas, the primordial fuel for forming new stars, is limited. Galaxies that manage to venture further into the void face a cosmic drought. Without the constant flow of gas from their neighbors or nearby filaments, their ability to create stars gradually diminishes. Could this condemn them to an early old age, transforming them into passive and dim galaxies long before their sisters in richer regions of the universe? Moreover, the gravitational gradient that exists at the edge of the void acts like a kind of invisible current. Galaxies close to the edge feel an attraction towards the denser regions, as if the very structure of the universe is pushing them out of the void. This phenomenon can cause galaxies to slowly drift towards galactic filaments over eons, altering the overall architecture of the cosmos. Thus, the Boötes Void is not just a desolate backdrop. It is a silent yet fundamental actor in the grand evolution of galaxies, marking the rhythm and destiny of those who dare to inhabit its edges. How do astronomers manage to measure something as intangible as the extent of a cosmic void? The answer lies in a fundamental tool of modern astronomy: redshift. But what does this term really mean? When a galaxy moves away from us due to the expansion of the universe, the light it emits stretches, shifting towards the red end of the visible spectrum. It's like the sound of an ambulance moving away, which seems to lower in pitch. Here, however, we are talking about light and unimaginable distances. By measuring how much that light has shifted, scientists can calculate not only the speed at which a galaxy is receding, but also its precise distance from Earth. How is redshift used to map a void like that of Boötes? Researchers observe thousands of galaxies in a region of the sky, carefully recording their redshift. If they detect a void of galaxies in a specific area, but the surrounding edges show many, they can infer the existence of a cosmic void. It's as if you were in a city and suddenly, while looking at a map, you discovered a huge park with no buildings in the middle of the urban sprawl. The absence reveals as much as the presence. Thus, each empty point on the three-dimensional map of the universe is identified thanks to the meticulous measurement of redshift. But how is the accuracy of these measurements ensured? Astronomers use highly sensitive spectrographs capable of analyzing the light from extremely distant and faint galaxies. by breaking down the light into its various colors, they can detect characteristic spectral lines that function like cosmic barcodes. When these lines appear shifted towards the red, they indicate the magnitude of the shift. By gathering thousands of these measurements, experts can construct a three-dimensional map where voids like Boötes literally appear as enormous bubbles of almost absolute nothingness within the galactic web. And why is redshift so crucial in the study of voids? Without this technique, it would be practically impossible to distinguish between an empty space and a mere optical illusion caused by distance. Redshift allows us to confirm that indeed, in certain regions of the cosmos, not only are nearby galaxies absent, but also distant ones, revealing the true magnitude of the void. Thus, redshift becomes the beacon that illuminates the deepest structure of the universe, allowing humanity to explore and measure spaces where, at first glance, there seems to be only darkness. Is it possible to study a cosmic void using only visible light? This is a fundamental question in astronomy, because while our eyes and optical telescopes allow us to peek into the universe, there are secrets that remain invisible in that range. The Boötes Void, by its very nature of extreme scarcity of matter, challenges conventional observation methods. How can we explore a region where almost nothing emits light? The answer lies in looking beyond the optical spectrum. Radio waves, for example, have become essential allies for astronomers. Although it seems incredible, even in a place where galaxies are extremely rare, traces of neutral hydrogen, the most abundant element in the universe, can be detected. Radio telescopes manage to pick up the faint emission of this gas, invisible to optical telescopes, thus allowing us to map the internal structure of the void and discover if there are clouds of dispersed matter or even hidden dwarf galaxies too faint to be seen in visible light. In addition to the radio spectrum, astronomers turn to X-rays and infrared to search for traces of activity in the Boötes Void. Infrared, for example, reveals residual heat from dusty objects or young stars that might be hidden behind gas clouds or too faint to be seen directly. X-rays, on the other hand, can indicate the presence of hot gas or extreme energetic phenomena, such as active black holes, that could exist even in such sparsely populated regions. Each of these observation windows acts like a specialized magnifying glass, capable of showing distinct and complementary aspects of reality. Why is it so important to explore at different wavelengths? Because the universe is like a great book, but each range of the electromagnetic spectrum reveals only one chapter. If we only use visible light, we would miss entire stories written in other frequencies. In the case of the Boötes Void, crossing these different observation channels has confirmed that it is indeed one of the most empty regions known, and has helped rule out the presence of hidden structures that would challenge our understanding of cosmic formation. Thus, exploration beyond optical observation not only expands the limits of our vision, but also reminds us how limited our knowledge would be if we relied solely on what our eyes can see. The Boötes Void then becomes a natural laboratory to demonstrate the power of multispectral astronomy, teaching us that sometimes the invisible holds more answers than we could ever imagine. What makes the Boötes Void so special compared to galaxy superclusters? To understand this difference, we first need to visualize the structure of the universe as a three-dimensional web, a cosmic spider web where dense regions filled with galaxies exist alongside others that are almost completely empty. Superclusters represent the nodes of this web, true galactic archipelagos where matter groups in astonishing amounts. In contrast, the Boötes Void is a vast expanse devoid of almost everything, a kind of cosmic desert where the presence of galaxies is exceptionally rare. If we compared the universe to a city, superclusters would be the busiest urban centers, full of activity and movement, while the Boötes Void would be a huge vacant lot with only a few isolated buildings. Did you know that in superclusters, thousands of galaxies can be found grouped in relatively small volumes, while in the Boötes Void, in a space of the same size, we would barely find a few dozen? This difference in density is so extreme that it is hard to imagine. In superclusters, the average distance between galaxies can be just a few million light-years, but in the Boötes Void, that distance multiplies by 100 or even more. But why do such marked contrasts exist in the universe? The answer lies in the cosmic formation process. After the Big Bang, small density fluctuations in the primordial soup of matter and energy led to regions that, over time, became increasingly dense, attracting matter and forming superclusters. Meanwhile, other areas remained almost empty, expanding and emptying even further, until they became voids like Boötes. It's as if the seeds of cosmic structure fell unevenly, leaving some places overflowing with galactic life and others steeped in complete solitude. This contrast is not only visually striking, but also has profound implications for the evolution of the universe. In superclusters, the constant gravitational interaction between galaxies favors mergers and the formation of new structures. In the Boötes Void, galactic isolation is almost absolute. The few galaxies that inhabit there evolve alone, unaware of intense external influences. Do these solitary galaxies behave differently? Evidence suggests they do, and their study helps astronomers understand how the density of the environment can alter a galaxy's fate. Thus, the Boötes Void and superclusters represent the opposite extremes of the grand architecture of the cosmos. One is the ultimate example of isolation, the other of galactic communion. Together, they reveal the incredible diversity of landscapes that exist beyond our small corner of the universe, and invite us to continue exploring the mysteries of that invisible web that holds everything together. At the limits of human knowledge, the Boötes Void represents a fascinating and enigmatic frontier. What secrets lie hidden in such a region devoid of matter? Although astronomers have mapped its extent and determined its impressive emptiness, many questions remain unanswered. For example, why is this region so extraordinarily empty compared to other areas of the universe? Is it possible that unknown processes during the formation of the cosmos intervened to create a void of such magnitude? Or are we simply facing a cosmic coincidence? One of the most intriguing mysteries is the precise nature of dark matter within these voids. If visible matter is scarce, what happens to invisible matter? Some models suggest that the voids could be virtually devoid of dark matter as well, while others point to the possibility that it exists in forms or quantities still undetectable with current technology. This uncertainty makes the Boötes Void a unique natural laboratory for studying the composition of the universe and testing our theories about gravity and matter. Furthermore, the existence of a few solitary galaxies within this void raises another series of fundamental questions. How have these galaxies managed to form and survive in such an isolated environment? Are they different in their structure and evolution compared to galaxies that inhabit denser regions? Studying them could reveal clues about galactic formation processes under extreme conditions and about the universe's ability to generate diversity even in the most inhospitable places. Finally, the Boötes Void challenges our understanding of the distribution of matter and the expansion of the universe. Are there even larger voids invisible to our current instruments? What role do these colossal voids play in the large-scale evolution of the cosmos? The absence of definitive answers keeps scientific curiosity alive and reminds us that, no matter how far we advance, there will always be frontiers waiting to be explored. The Boötes Void is, ultimately, a permanent invitation to look beyond and to ask ourselves what other wonders and mysteries await in the most remote corners of the universe. Why is the night sky dark if, in theory, there are billions of stars in every direction? This is the famous Olbers paradox, a question that has intrigued scientists and thinkers for centuries. If the universe were infinite, static, and uniformly populated by stars, every point in the sky should be illuminated by the light of a star, making the night shine as brightly as the day. However, when we go out at night and look up, what we see is mostly darkness. How can this apparent contradiction be explained? One of the keys to solving Olbers' paradox lies precisely in the enormous cosmic voids, such as the Boötes Void. These regions, almost completely devoid of galaxies, act as vast spaces of silence in the universe, interrupting the continuity of starlight that could, in theory, flood our sky. The voids are not just areas without visible matter, but also without significant light sources. Therefore, they contribute to keeping large stretches of the sky dark, even in a universe filled with stars. Moreover, the universe is neither static nor eternal. It is expanding and has a finite age. The light from many stars simply hasn't had enough time to reach us. And in the regions where it could have arrived, it often encounters these voids, which function as cosmic deserts, further diminishing the amount of light that reaches us. It's like trying to light up a huge room with just a few candles scattered in the corners. Most of the space would remain in shadow. Ultimately, the existence of voids like Boötes is crucial to understanding why the night is so dark. Far from being mere anomalies or oddities, the voids are an essential piece of the cosmic puzzle. They show us that the darkness of the sky is not an inexplicable absence, but a direct result of the structure and evolution of the universe. Thus, Olbers' paradox ceases to be an absolute mystery and becomes a fascinating window into the true nature of the cosmos, a place where light and shadow coexist, shaped by the immensity of intergalactic voids. The Boötes Void is much more than just a simple region devoid of matter. It is a true cosmic enigma that has puzzled astronomers for decades. Why does such an enormously empty space exist in a universe where matter tends to clump together? One of the greatest anomalies surrounding the Boötes Void is its size. There are voids throughout the universe, but very few reach these dimensions. With a diameter of hundreds of millions of light-years, it surpasses any simple explanation based on the standard evolution of cosmic structure. This void is so vast that if the Milky Way were at its center, we would not see any other galaxy in any direction, as if eternal night had taken over everything. But the mysteries do not end there. One of the most intriguing questions is why, although physics predicts the formation of voids, the Boötes Void seems to be too empty, even by modern cosmology standards. Computational models suggest that there should be more matter scattered within it, even if in the form of small galaxies or faint clusters. However, observations have revealed a surprising scarcity, much less than expected. Is it possible that unknown processes have cleaned this region? Some scientists have even suggested that phenomena like dark matter or dark energy may have played a special role in its formation, altering the distribution of matter in ways we do not yet fully understand. Even more puzzling is the existence of a few solitary galaxies within the void, true cosmic castaways in a sea of nothingness. These galaxies exhibit unusual properties. Some appear to have evolved in isolation for billions of years, without significant interaction with their neighbors, challenging our ideas about galactic formation and evolution. How have they survived in such a hostile environment, without the cosmic food provided by gas-rich filaments and matter? Could they hold clues about the early stages of the universe, preserved by their extreme isolation? So far, these questions remain unanswered. As if that weren't enough, some measurements of the cosmic microwave background have shown slight anomalies in the direction of the Boötes Void, as if the presence of this colossal void subtly altered the relic radiation from the Big Bang. This phenomenon, known as the integrated Sachs-Wolf effect, suggests that light traveling through such a matter-deprived region undergoes tiny changes in its energy. Although the evidence is still a subject of debate, it raises the possibility that the Boötes Void is not only a spatial void, but also a visible imprint on the energetic history of the universe. Thus, the Boötes Void remains a frontier laden with enigmas, reminding us of how much we have yet to discover about the true nature of the cosmos. Who would have thought that such an empty place could captivate the human imagination so much? The Boötes Void, although it is a region almost devoid of galaxies, has managed to seep into popular culture and art, transforming into a symbol of cosmic mystery and solitude. Why does the idea of such a vast and at the same time desolate space attract us so much? Perhaps because it forces us to confront the magnitude of the universe and questions that go beyond science. In science fiction literature, the Boötes Void has been used as a setting for stories of exploration and encounters with the unknown. Some novels imagine spaceships crossing this region, facing absolute silence and a sense of isolation, as if traveling through a cosmic version of an endless desert. What could be hidden in a place where there is almost nothing? This question has inspired numerous tales, from hidden civilizations to enigmas that challenge known physical laws. Cinema and documentaries have also seized the opportunity to mention the Boötes Void. Movies and series have referred to it as the extreme example of nothingness, a visual and narrative reminder of how small we are in the face of the universe. Even in some space exploration video games, the Boötes Void appears as a forbidden or mysterious zone, where players must confront the total absence of resources and signs of life. The mere mention of its name often generates an atmosphere of unease and wonder, as if alluding to an unfathomable abyss. It is also curious how this void has become a metaphor in contemporary art and philosophy. Writers and thinkers have used the Boötes Void to discuss existential emptiness, deep loneliness, or the human desire to find meaning amidst the immensity. The image of such an extensive region, almost completely devoid of matter, serves as a starting point to reflect on humanity's place in the cosmos. Isn't it fascinating that something so seemingly insignificant as an empty region of space can inspire so many ideas and emotions? Over the years, the Boötes Void has shown that even nothingness can have a profound impact on the collective imagination. From speculative fiction to the most abstract philosophy, this corner of the universe has left its mark on popular culture, reminding us that emptiness can also be filled with meaning. How far can we go in studying the Boötes Void? Currently, astronomical technology is advancing by leaps and bounds, and each new instrument allows us to peek a little deeper into the secrets of the most uninhabited regions of the cosmos. Next-generation telescopes, such as the James Webb and increasingly powerful radio telescopes, are opening windows to wavelengths that were previously inaccessible, enabling the detection of subtle traces of matter and energy within the vast voids. Will these instruments be able to find remnants of even fainter galaxies, or signals of unknown physical processes in the depths of the Boötes Void? The future of research in cosmic voids not only depends on looking further, but also on looking in completely new ways. Artificial intelligence algorithms are being developed that can analyze mountains of astronomical data and uncover patterns invisible to the human eye. This digital revolution, combined with collaboration among observatories around the world, promises to accelerate the discovery of unsuspected phenomena in the Boötes Void and other similar voids. What would happen if one of these artificial intelligences finds anomalies that challenge current theories of cosmology? Moreover, scientists plan to employ new three-dimensional mapping techniques using the redshift of millions of galaxies to reconstruct the internal structure of the voids with unprecedented precision. In this way, it will be possible to understand not only the boundary of the Boötes Void, but also how it interacts with neighboring galactic filaments and how it evolves over time. It's as if we have an increasingly detailed map of an immense and mysterious ocean, where each expedition reveals new islands, currents, and whirlpools. Equally exciting is the prospect of experiments aimed at tracking dark matter and dark energy, two fundamental components for unraveling why such gigantic voids exist in the universe. New space missions, such as Euclid and the Vera Rubin Observatory, aim to accurately measure the distribution of matter and energy on a large scale, and perhaps they can answer one of the most intriguing questions. Are voids like Boötes simply empty spaces, or do they contain essential clues about the most exotic ingredients of the universe? The path that lies ahead for cosmology is as vast and deep as the Boötes Void itself, and each advance brings us a little closer to understanding the true nature of the cosmos. What does it take to unravel one of the greatest enigmas of the universe? No one can do it alone. The study of the Boötes Void has driven collaboration among scientists from all over the planet. Astronomers from America, Europe, and Asia have joined forces in multidisciplinary teams, combining telescopes, databases, and theoretical models. Why such a collective effort? Because the Boötes Void is so vast and mysterious that even the most advanced instruments of a single nation could not fully encompass it. Measuring, mapping, and analyzing a void of such proportions requires a symphony of resources and brilliant minds working in unison. Large international collaborations have allowed for the sharing of data obtained from various observatories, such as the Sloan Digital Sky Survey in the United States, the Very Large Telescope in Chile, and the Arecibo Radio Telescope in Puerto Rico when it was still operational. By sharing information and coordinating observations, scientists were able to build a more accurate picture of the Boötes Void, overcoming the limitations that any team working in isolation would face. These alliances have been essential, not only in discovering the extent and structure of the void, but also in identifying the few galaxies that inhabit its interior. Does competition between countries disappear when it comes to exploring the cosmos? To a large extent, yes. The desire to understand the nature of the universe transcends political and cultural boundaries. Joint projects like the European Southern Observatory, the European Space Agency, and collaborations with NASA have made it possible for data to flow efficiently and for results to be reviewed and validated by experts from different parts of the world. In this way, science becomes a universal language, and the Boötes Void a challenge that unites humanity under a single question. What secrets does this cosmic colossus hold? International congresses, symposia, and scientific publications have become true meeting points for experts in cosmic voids. How is research of this magnitude coordinated? Through digital communication networks, shared databases, and open platforms where findings are made available to the global community. In this way, knowledge advances rapidly and collaboratively. The Boötes Void is, in a sense, a mirror of human cooperation, an apparently empty region that nonetheless has filled the minds of those who dare to study it together with questions and discoveries. Why does a region as desolate and empty as the Boötes Void fascinate the human mind so much? The answer lies in our curious nature and our desire to understand the unknown. The void, that almost total absence of matter, not only challenges scientific knowledge, but also awakens deep philosophical concerns. How can such a vast space exist while being so practically empty? This question resonates within us because, in many ways, confronting the cosmic void is like looking into an existential mirror. It forces us to question our place in the universe and confront the immensity of nothingness. Since ancient times, humanity has felt a mix of fear and wonder at the concept of the void. For some, it represents horror vacui, the ancestral fear of absence, of meaninglessness. What does the void tell us about what it means to exist? When we contemplate regions like the Boötes Void, the mind is compelled to grapple with ideas that far exceed our everyday experience. If the universe is mostly composed of empty spaces, is nothing then more common than something? This paradox leads to reflections that have inspired both philosophers and scientists throughout history. The Boötes Void also challenges the common perception that the void is synonymous with insignificance. In reality, its existence is fundamental to the structure of the cosmos. If we think of the universe as a sponge, the voids would be the large gaps that allow filaments and galactic clusters to connect and organize. But how does this affect our view of the world and ourselves? Knowing that most of the universe is made up of voids can make us feel small, but it can also awaken a sense of wonder at the improbability of our existence in the matter-filled corner we inhabit. Ultimately, the void is a powerful metaphor for the human mind. Just as the Boötes Void is a region of hidden possibilities, the mind also harbors unexplored spaces, unanswered questions, and potentials yet to be discovered. Is it possible that the void, rather than representing absence, symbolizes the opportunity to understand something new? Deep down, confronting the immensity of the cosmic void is also confronting our own limits and the eternal search for meaning in a universe that, at first glance, seems indifferent. However, it is precisely in that search where the greatness of humanity resides. What can an immense void in the universe teach us? Perhaps more than we imagine. The Boötes Void, that vast region where silence and nothingness reign, offers us a valuable lesson about the very nature of the cosmos. When we think of the universe, we often imagine it brimming with galaxies, stars, and planets. However, there are places where there is almost nothing, where cosmic loneliness is the norm. The Boötes Void reminds us that the universe, for the most part, is composed of empty spaces, and only a fraction contains the visible matter we know. This apparent desolation forces us to rethink our perspective. Absence is also a fundamental characteristic of reality. Why is it important to study something where there is almost nothing? Here arises one of the deepest teachings. Cosmic voids, like Boötes, are natural laboratories for understanding how matter is distributed, how large structures emerged, and how the universe evolves over time. By analyzing these spaces, scientists can test hypotheses about dark matter, cosmic expansion, and the dynamics of dark energy. Even the mere existence of such uninhabited regions challenges our most basic theories about the origin and fate of the cosmos. Investigating the void shows us that sometimes the key to understanding what exists lies precisely in what is missing. The Boötes Void also raises fascinating philosophical questions. What does it mean that there are such lonely places in such a vast universe? Are we a fortunate exception, surrounded by matter and life, or just a casual detail in a sea of emptiness? The existence of regions so devoid of galaxies compels us to reflect on our position in the cosmos and the value of rarity. Just as a single island stands out in the midst of an endless ocean, our galaxies shine in the immensity of nothingness, giving a new meaning to the word precious. Finally, the Boötes Void teaches us not to underestimate the importance of absence. In music, the silence between the notes is as significant as the notes themselves. In the universe, voids allow structures to stand out, galaxies to cluster, and cosmic evolution to continue its course. By understanding the existence and role of these spaces, we discover that the universe is not just a collection of objects, but also the story of the intervals between them, of the limits, of the invisible boundaries where physics writes its rules. Ultimately, the Boötes Void invites us to contemplate the value of emptiness, both in the cosmos and in our way of understanding reality. The universe is an immense place, but few of its corners evoke as much wonder as the Boötes Void. Why should we be interested in such a desolate region, where there are almost no galaxies, stars, or visible matter? The answer lies in the contrast. The Boötes Void brutally and silently shows us that most of the cosmos is, in fact, empty. If the universe were a city, Boötes would be that vast and silent neighborhood that separates the bustling areas, reminding us how extraordinary it is to live in a region full of light and matter. Can something so empty teach us about the nature of everything? Surprisingly, yes. Cosmic voids like Boötes act as mirrors of the primitive universe, preserving clues about the evolution of space and time. They are the footprint of colossal processes, such as cosmic inflation and accelerated expansion, that have sculpted the cosmic web. To ask why such a vast and matterless area exists is, at its core, to ask about the origin and destiny of everything we know. The Boötes Void serves as a natural laboratory where the laws of physics can be observed under extreme conditions, far from the interference of galaxies and ordinary matter. At first glance, it might seem that such an empty region lacks importance, but science reveals the opposite. The study of these voids has allowed astronomers to test cosmological models, explore the role of dark matter and dark energy, and better understand the architecture of the universe. Voids are not mere gaps, they are the result of deep forces, the invisible dance between matter and energy on inconceivable scales. What mysteries does the Boötes Void still hide? Could its boundaries reveal new particles, unknown physical laws, or even clues about the ultimate fate of the cosmos? Contemplating the Boötes Void presents a fascinating paradox. The more we learn about the void, the better we understand the fullness of the universe. The existence of such uninhabited regions invites us to reflect on our place in the cosmos and to appreciate the rarity of matter, life, and consciousness. Will we ever be able to unveil all the secrets that this cosmic abyss holds? In the meantime, the Boötes Void remains there, a silent reminder that in the vastness of space, the greatest mystery may be found in silence and absence.